All right, so this presentation will talk about enthalpy. So our lesson objectives, we're going to start by defining enthalpy, which is given by the uppercase capital H. We'll define exothermic and endothermic reactions. We'll define thermochemical equations, and then we'll use Hess's law to calculate heats of reaction, or delta H Rxn, from thermochemical equations. Thermodynamics is the study of energy conversions between heat and other forms of energy. The total heat content of the system is called enthalpy, given by the capital letter H. Enthalpy is equal to U plus PV. U is the internal energy of the system, which includes the sum of the kinetic energy of those molecules. This includes all the ways that the molecule can move. Therefore, gases have much more energy than liquids, which have much more energy than solids. And that's just due to the increased number of ways that a gas can move over a liquid, which can move in more ways than a solid. To account for all of the heat energy, you also have to include the amount of work the system has done, thus the PV portion. So P delta V is the amount of work you can do. When enthalpy is greater than zero, so the enthalpy change is greater than zero, the reaction is endothermic. Additional energy is needed to perform the reaction. When the enthalpy is less than zero, the reaction is exothermic and the reaction releases heat, so the reaction vessel feels hot. If the pressure and volume are constant, then the enthalpy change in the system is equal to the amount of heat energy released or absorbed in the system. This is the case when you do a chemical reaction, but do not attempt to do work with the heat evolved, which is pretty much every calorimetry experiment ever. Let's take a slight little detour and talk a little bit more about work. And internal energy is equal to the heat plus the work. Is the ability of matter to move against an opposing force. Generally, that a force is applied by expanding gases pushing against the atmosphere. In fact, for us, that's going to be true. Thermodynamics started with the study of steam engines. Physicists can deal with other work, like pushing things up an inclined plane or that sort of thing, but we chemists will stick most of the time to studying what pistons will do. So, the expansion of gases to push a piston up and get train wheels to roll or cars to move is the type of work we're talking about, and this can be expressed as pressure times the change in volume, or P delta V. The pressure here being the atmospheric pressure, which is what is resisting the motion. So we're going to try applying some of the ideas to phase changes. Mainly we want to do exothermic and endothermic along with these concepts. So is the enthalpy of melting an ice cube positive or negative? And is that endo or exothermic? When you're melting an ice cube, we know that we have to add energy to it. So if we're adding energy, that is positive. And if it's positive, then the sign makes it endothermic. Is the enthalpy of condensing ethanol and it's still positive or negative? And is that endo or exothermic? So if you are condensing something from gas phase down to liquid phase, you have to take energy out. The sign of taking things out is negative, and that makes it exothermic. Our primary application of enthalpy, which we're also going to use with calorimetry, but different topic, is going to be when using Hess's law. So Hess's law says that the enthalpy change of a process is equal to the sum of the change in the enthalpy of the component steps. So what does that mean? In the lab, you've made a product using a two-step synthesis. You know that you can combine the equations for those two steps into an overall equation for the reaction. We're going to do the same, but for what's called thermochemical equations. So when we do it, reactant side will go to reactant side, product side will go to product side, and thermochemical value will add to thermochemical value. So when you did this for your two-step synthesis, you went through a process of two or more steps, but you summarized it with one equation. But why can we do this? Enthalpy is a state function. The value of a state function is only dependent on the physical state of the thing, solid, liquid, gas, aqueous. So examples of state functions include enthalpy and internal energy, which we talked about in this presentation, but also elevation. Height of a mountain does not depend on how you got up the mountain. Anyway, there's also a bunch of other things that you'll see in 108 if you decide to take that course. So this is the why. No matter the way that you get to the overall equation, the value will be the same. Let's talk about the how. This brings us to thermochemical equations, which are chemical equations with a thermochemical value attached on the end. That's right, enthalpy is now part of the chemical equation. So if you want to manipulate the equation, you must also manipulate the enthalpy change associated with the equation. So in this case, we have an example of zinc solid plus hydrochloric acid making zinc chloride and hydrogen gas. And it has a delta H associated of negative 153 kilojoules. All right, well, what if we needed to multiply by a coefficient? Well, when we do that, we're going to multiply the entire thermochemical equation by the coefficient. So that's going to include the delta H. So I've put my parentheses around the entire thing. I distribute the 2 through all the way, and my delta H now becomes negative 306, which is double negative 153. All right, now what if we needed to flip this reaction around? Products become reactants, reactants become products. In that case, we flip the sign of delta H. Why? Because we need to conserve energy. So if one way releases energy, then the other way has to absorb the energy in an equal and opposite amount in order for law of conservation of energy to apply. So let's apply this tidbit to Hess's law for a multi-step process. Acetic acid is contained in vinegar, which is a solution of acetic acid and water. Suppose acetic acid is formed from its elements according to the following equation. 2 carbon atoms in graphite form plus 2 hydrogen gas plus oxygen becomes acetic acid. Find the enthalpy change, delta H, for this reaction using the following data. So we're given information about acetic acid plus oxygen making carbon dioxide and water, combustion reaction. We have carbon plus oxygen making carbon dioxide. And we have hydrogen and oxygen making liquid water. All right, so first thing we want to do is line things up so that our products are on the product side, our reactants are on the reactant side. And so if we look at our first equation, A, we have a reactant of acetic acid, but we need it to be a product. So we're going to have to flip that equation. And if we flip the equation, we flip the sign. So that's our new manipulated equation A. Now we go to equation B. And in equation B, we have the only source of carbon in graphite form of any of these equations. We have 2 moles of it in the equation we want. So we're going to multiply that entire equation B by 2. And finally, we go down to equation C. And this is our only source of hydrogen gas. We have 2 moles of hydrogen gas in our target equation, so we're going to multiply all of C by 2. So this is just a process of looking for the things that you need and making sure they are in the place that you need them and in the quantity that you need them. So ask yourself, is this on the right side? Are there enough of them? All right, so now we go on to the next step. Okay, so we're going to take our 3 modified equations and add product side to product side, reactant side to reactant side, just like we did with redox half reactions when we put them back together, just like we did with the 2-step synthesis. But now we have a thermochemical equation. So we're going to add our DHs together as well as our reactants and products. So we do that and we get a really long looking thing. But we're going to simplify it. So we're going to go through and we're going to cross off stuff that's the same on opposite sides. Okay. And once we have done that, and we've added up all of our delta H's, We get our target equation. Yay, we did the thing. And now we have a delta H of negative 486 kilojoules. So it worked. Good for us. There were a couple steps. There were lots of things to do, but it worked out in the end. So to summarize, enthalpy is given by capital H. It's equal to the internal energy of the system plus pressure, volume, work. And it represents the total heat of a system. Internal energy is equal to, or is represented by capital U, and it's equal to Q, which is heat, plus work, which is the PV again. When enthalpy is greater than 0, the reaction is endothermic, and additional energy must be added to perform the reaction. When enthalpy is less than 0, the reaction is exothermic, and the reaction releases energy. A state function means that the value of the state function is only dependent on the state of the material, i.e. solid, liquid, gas, or aqueous. A thermochemical equation is a chemical equation with a thermochemical value attached at the end. And finally, Hess's law says that the enthalpy change of a process is equal to the sum of the change in enthalpy of component steps.